Next, let's look at the product rule, which is on page 253. The product rule is how you differentiate something that multiply together. So far we have said that when it comes to addition and subtraction, which is straightforward, when you take the derivative of something that's added up, you just take the derivative of each one and then add it up. Now what about the product? Well, the product is what happens when the two functions are being multiplied together. Do you just take each one and then multiply together? No, the product rule gets more complicated. So basically the product rule is, let's say you have two functions, f and g, and you're multiplying them together. And how do you take the derivative of f and g? The derivative of f and g is is basically, say, I'll use the prime. The prime means let's take the derivative. That to take the derivative of a product, what you do is you take the derivative of the first and then multiply by the second, plus take the derivative of the second multiplied by the first. So it's f prime g plus g prime f. And it's somewhat symmetrical, so it's fairly easy to remember the product rule. Having said that, I'm writing it this way so it's simpler and it's easier to remember. Then, of course, the official way of writing it is quite a bit longer, such as such as the way your book has it. If j of x equal to f of x times g of x, then j prime of x equals to f prime of x times g of x plus g prime of x times f of x. So it's slightly more wordy, but it says the same thing, but maybe in a more detailed way. Now, to prove the product rule, let's go to the next page. We are on page 254 to prove the product rule. And the proof is somewhat similar to the time when we proved the differentiation proves continuity, where we added something and then subtracted it right away, and then that somehow make things come out. So to prove the product rule, like we proved all the others, we pull back our old definition and then try to get something out of it. So here's the definition, right? So if, let's say your j of x, we'll call j of x equals to f of x times g of x. This is a multiplication relationship here. So j prime of x, by definition of the derivative, equals to the limit as h approach 0 of the function. This is the entire function now. The whole function at x plus h, which means f of x plus h times g of x plus h. Because now, by definition, this thing we have to do the x plus h point minus just the thing itself, which is f of x times g of x. Oops. And then the whole thing divided by h as h approaches 0. That is the definition of the derivative of j. So having done that, okay, that's nice. What are we gonna do with this? How do we get from here to here? Now, so then the next point, we're gonna pull that trick I mentioned. We're gonna add and subtract something. Specifically, we're gonna add and subtract f of x and g times g of x plus h, like this. Now, this is gonna be a lot of symbols and writing, but just patiently look at it until you read through the whole thing, okay? And it's just yeah, lots of writing, lots of symbols, but it's still straightforward. So we will pull that stunt equals to, write this stuff out, h approach 0. We still have this, so we write the first one, f of x plus h, g of x plus h. All right, so far so good. We're going to pull this trick, which is we're going to minus f of x times g of x plus h. And why are we minusing that? Because that's going to help us get here. So this is something that somebody stared at it and tried different things, and this one turns out to work. So let's continuing. Plus, being that we subtracted one, we have to add one to be fair, right? So that the equation holds g x plus h. And then minus. Okay, so we added one, we subtracted one, and then added it back, so nothing changed. Then we add this last term, minus f x g of x. Now we have, and this whole thing will be divided by h. Now so far we have only added and subtracted, subtracted and added some, and the same thing. So we haven't changed anything. But to do that, however, should help us get there. At least that's the hope. So let's look at this. Then we'll break this into two chunks. So rewriting this thing, so far we still haven't done anything incredible. But we'll just rewrite this into two fractions, which will take a lot of writing. So let's take our time. We got all kinds of time. So copy this thing down again. F of x plus h, g of x plus h, minus f of x, g of x plus h. Okay, that's the first half. We right now we're just breaking it into two fractions. That's the first half, and then plus the limit h approach 0. The second half of this thing, f of x times g of x plus h, minus the last item, x g of x, divided by h. Okay, so now so far we have done a simple thing that is nevertheless requires a lot of writing. So far so good. Next, we will next we are going to factor, because this particular this thing here has g of x plus h on both items, so we will factor it out. Now, which is a simple thing to do, but a lot of writing, so let's patiently write it out. So it equals to limit h approach 0. We'll factor this thing out, which is f of x plus h minus f of x divided by h. And this whole times, okay, this parentheses times g of x plus h. All right, and then plus, and we'll do a similar thing over here. This thing has f of x as the common factor, so we will take that out and yeah, do that. So plus limit h approach 0. So far we're just going to factor out one thing. All right, so f of x, what are we factoring? No, we won't write it this way. We'll write it f of x at the end. For anyway, yeah. So we'll factor out f of x and put it at the end. So what we have left after factoring out f of x, we will have g of x plus h minus g of x divided by h. And then this whole thing will be multiplying by f of x, which we factored out, since there's one here and one here. All right, so far we have done a very simple factoring that involves a lot of writing. All right, and at this point, so now what? Now here's where the magic happens. Now you look at this thing. All right, the limit of these two things, what is that? That is the definition of f prime of x, this thing right here. Okay, so this is f prime of x. And as h goes to 0, this goes to g of x. G of x, okay, plus over here, this is the definition of g prime, the derivative of prime. See, the limit h approaches 0, g of x plus h minus g of x of h. That's the definition of the derivative of g at x. So that is g prime of x times f, that's just f of x. It doesn't even have an h in it. So we're good. Times f of x. And that is the proof of the product rule. And of course, the product rule has certain basic requirements. For example, the f and g has to be differentiable, right? Otherwise, what are we talking about? We can't take a derivative if it's not even differentiable. But assuming all the background requirements are met, then this is called the product rule, and it's important for you to memorize it. It's fairly easy to memorize. It's f prime g plus g prime f. And it doesn't matter which order you say that. That is the prime of one multiplied by the original function of the other plus the prime of the other function multiplied the original function of the first. Something like that. And that is the proof of the product rule. So now I will erase the board. Now, having finished proving the product rule, let's look at some of the examples of how we might use it. Example 3.23, that seems fairly straightforward, so I'll leave that as a homework. So let's move on to example 3.24. 3.24 says that we have a product, okay? And then let's use the product rule to figure out what the derivative is. Now, it says apply the product rule to binomials. What's a binomial? A binomial is something that has two terms, such as x squared plus 2 in the example. That's a binomial. And the other thing, 3x cubed minus 5x, that's another binomial. It's just a name that has no real significance, I think. But doesn't matter. That's in case you wonder can't remember what a binomial is. So now we have our binomial. We need to apply the product rule. So let's do that. First, write down the problem. J of x equals to the two binomials, x squared plus 2 times 3x cubed minus 5x. And first, so we need to find the derivative of j. And remember, what is the product rule? The product rule says j prime equals to f prime g plus g prime f. Okay, that is how you can quickly remember it. That's a j. Anyway, so and following that rule, we will do so j prime of x equal to f prime. That's 2x. That we'll consider that f times the second result, 3x cubed minus 5x, and then plus derivative of the second, which is 3 times 3 is 9, applying the power rule or something, 9x squared minus 5. All right, and that would be that's just g prime, and we still have to multiply by f x squared plus 2. All right, so that's our that's j prime. But right now we will do a little bit of algebra to clean stuff up, shorten it, simplify something, and hope that not mess up the multiplication, the basic math. Okay, with the hope of not. So let's now do algebra. That's 6x fourth If you can't remember how to do any of this, please look it up. Minus 10x squared plus, and this takes even longer, times this. What was the name for this? Anyway, so each item in this group has to multiply by each item in the other group, but not within this group. So we have 9x to the power 4th minus 5x squared plus 18x squared minus 10. All right. So that is 6 plus 9 is 15. So far, so good. We have 15x to the power 4th. And then x squared, we have minus 10 minus 5, that's minus 15, plus 18 is plus 3. So we have plus 3x squared. And lastly, the numbers. We only got this, minus 10. And that is j prime. That is, if you have two things multiplied together, you can calculate the derivative this way. It's you can, of course, also just multiply that out and then calculate the derivative too. But sometimes the product rule might be easier. Yeah. Anyway, the product rule works, as we have proven. Having said that, let's do the next thing, which is called the quotient rule. The quotient rule means, now that we know how to take the derivative of something that multiplies together, what if it's in a division situation? That is, let's say j of x equals to f divided by g. F of x divided by g of x. Okay, in that case, what is j prime? And unfortunately, it doesn't just mean derivative of f prime divided by g prime. It's not so simple. In fact, it doesn't even look like that. It's a little more complicated than that. So what happens is that j prime, if j is f over g, then j prime, that is the derivative of j, equals to something like this. Equals to g times derivative of f minus f times the derivative of g over g squared. That's which is quite a bit involved. Is the bottom times, the way I remember it is, I call it the bottom takes the derivative the bottom times the derivative of the top minus the top times the derivative of the bottom, all over bottom squared. You might not find that really a big improvement. I find it helpful to remember it that way, but maybe you can come up with a better way to help yourself remember the quotient rule. The quotient rule is not proof in the book, so we will also skip it and just go right ahead and try to apply this thing. Example 3.25. Next, let's look at example 3.25. Which is on page something. Let's see, we are right now on page 255. Yeah, okay. 255. And the example we're going to do is, for the first example, we'll do a fairly simple one, where k of x equals to 5x squared divided by 4x plus 3. Now, you see, it's just a simple example that they made up quickly. 5, 4, 3. And x squared, x, and nothing. So, and now that we have a simple little example, let's see if we can get it to work. We'll erase this part because to give us a little more space. All right. Now k prime, then what is k prime? That is, what is the derivative of k with respect to x? So k prime of x equal to applying the quotient rule, which is somewhat involved, but can still be done. And the way I remember it is take the bottom plus times the derivative of the top. The top is 5x squared, so that derivative is 10x minus, don't forget the minus. The minus actually makes it harder to do than the plus in the product rule. But you gotta, what can you do? That's the way it is. So bottom times the derivative of the top minus top, which is 5x squared. I'll write it this way. Top times the derivative of the bottom, which is just 4. And the whole thing has to be divided by the bottom squared. 4x plus 3. Following this particular formula. And that's about it. That's the derivative. Of course, that's not all, because we have to do some algebra to simplify that thing, right? Simplifying, which means we have to do some grunt work, but in calculus, sometimes grunt work is required. And so we will patiently do the grunt work, which gives us something like all right. I'll write down the denominator first, and then the numerator, we have 4x times 10. That's 40 minus 5 would be 5 times 4. That's 20. So 40 minus 20 is 20. So we have 20x squared plus, that's 30x. 3 times 10 is 30. So 30x. And that should be good enough for anybody, right? So that's the quotient rule. Now the quotient rule is going to be more tedious to apply the more your fraction is, right? Because so you might get the quotient rule can become fairly involved, but the method of applying it is straightforward. You take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, and then you sit down and work on the algebra and to simplify. And that's about all there is to the quotient rule. Next, let's use the quotient rule to prove a neat little theorem. The next theorem on page 256 is theorem 3.7. The theorem 3.7 is similar to what we have already proved in the power rule, that is the derivative of something that is x to the power k, okay? The derivative of x to the power k is the same as x to the power k minus 1. And you say, isn't that the power rule? Yes, but actually the power rule we only proved it for positive integers of n. Now what if your k is negative? It's some kind of negative number. We didn't prove it for any negative numbers, but we're gonna do it now. That it just happens that even if the exponent, the number up here is negative, the power rule still works. So it's very, very neat. And the proof is also fairly simple because we already have the quotient rule. So what happens is that we let k, being that k is a negative number, we let k equal to minus n, where n is a positive number, right? So then in reality, the k to the power n, which is what we're trying to take the derivative of, is something that actually looks like this. Is x to the power n. Is 1 over x to the power n, where n is positive. Okay, so but still, how are we going to take the derivative of this? Well, this is a quotient, strictly speaking, right? There's only 1 on top. It's just a number, but still it is a quotient. So we will apply the quotient rule on this thing. So applying the quotient rule, we have the derivative, therefore, is we'll write it this way: d of 1 over x to the power n by dx. Okay, that means take the derivative of this thing is, by the quotient rule, the bottom times the derivative of the top, which happen to be 0 because the top is a constant. Derivative of the constants are zeros, minus the top, which is 1, times the derivative of the bottom, which is nx n to the power n minus 1. That is by the power rule. And the whole thing will be divided by the bottom squared, x n squared. All right, so that's the derivative. Now we'll clean it up a little bit. And that says that's 0, so that nicely disappeared. And so we just have to, we have a negative sign, which we cannot get rid of. And then we have the n. And then there's xn minus 1. And then xn squared. That is, so by the time you get, so that equals to x to the power n minus 1 minus 2n. Okay, which is what? That is the same as minus n x to the power n minus 2 minus n minus 1. All right, so at this point, we go back to k. So what was n again? N is just, we already said k equals to minus n. So you put k back, k is minus n, so that replaces that minus n. X, that's k, k is minus n minus 1. And that is neatly what we're trying to prove. Which shows that the power rule works, okay, whether the power itself is positive or negative. You just can blindly use the power rule regardless of what the power is. So that's very nice that way. And in this case, we're only talking about the power as an integer, positive or negative. Next, let's look at example 3.26, which I will leave as homework because it's short and sweet and fairly straightforward. And I don't think you will have too much trouble understanding or doing it. And 3.27, following the page, is the same. A quick, short, and sweet application of the extended power rule and the constant multiple rule. Doesn't matter what they're called, just remember how to do it.